each of the potential energies that we've come across has a force associated with it. But it's not necessarily true that every single force has a potential energy associated with it. The forces that have a potential energy associated with them are called conservative forces. Another way of saying this is that the work done by a force is independent of the path that you move the object along. A good example of a force that is not conservative, that is path dependent, a force that does not have a potential energy associated with it, is the frictional force. And let's just consider that case. So let's say that we have a block and we're going to slide it along a surface where there's some frictional force. So we're going to move the block some distance, delta x. And as we're sliding it, there's going to be a frictional force in that direction. So the work done by the frictional force, let's see, since these two are in opposite directions, we're going to have negative work done, so negative F delta x. So we have our block over here, and let's move it back to our starting position. So we're going to move it back this way, the same distance, delta x, but as we're sliding it this time, the frictional force will have changed directions and will be pointing back this way. So again, the work that we do will be negative F delta x. So the round trip, the work done round trip, starting here, moving over here and coming back, is going to be negative 2F delta x. So this is an example of a force that has a path-dependent work. An example of one that's not path-dependent would be the gravitational force. So we consider that example, and let's say I have a ball, and as we move it up some distance delta y, the work done by gravity, going up, well, in this case, the force of gravity is down, so the work done by gravity as you lift it up is negative F grav delta y. Now if we go ahead and move the ball back down to the starting position, delta y again, gravity is still down, the work done going from here down is a positive F grav delta y. So if we combine these two to find the total work done by gravity when we lift the ball up and bring it back to its starting position is 0. So that means the work is independent of the path. We could take any path we wanted. We could go all the way up here and bring it back down. We'd still have 0 work done. But in the case of friction, it's going to depend on how far over we move and then bring it back. The key here is that these forces don't change direction depending on which way we're pushing. With friction, it does change direction. So we have, in the case of friction, a force that depends on which way we're pushing, and so the work done going one way doesn't cancel the work done going back the other way. So friction is a good example of a force that doesn't have a potential energy. Another example, of course, is air resistance. So hopefully this kind of gives you an idea. This section is primarily important in understanding why some forces have potential energies and why some forces don't.